Okay, let's get going for this morning. Just to give you a recap of what we finished on last time, we were looking at mixed strategies. The idea that sometimes players don't always do the same thing. That they don't choose definitively. In the game that we saw last week, with the game of matching pennies, they don't always choose heads or tails. And indeed, we showed intuitively that sometimes it makes no sense whatsoever to play a pure strategy in games that look like this. And the way that we went through to solve these games was by use of the best response lines. We did this for our two players, if you can remember, Bill and Ben. And we traced out the best response lines for Ben, we traced it for Bill, and then where they intersected was where our Nash equilibrium was. And we said in this game that we set up, there was a unique Nash equilibrium in mixed strategies. And that mixed strategy Nash equilibrium was where both players chose over their respective strategies whether to choose heads or tails with the probability of 1/2. And that was our mixed strategy Nash equilibrium. But in this game, there was only one Nash equilibrium because these best response lines only cross in one place. So there's only one outcome where both players are choosing a best response. And where all players are choosing the best response, that accords with our notion of a Nash equilibrium. What I now want to do, just to finish off this idea of mixed strategies, and it's very, very important, because in an exam, a typical question that I'm going to be able to ask you is to identify the mixed strategy Nash equilibrium, to draw the best response lines. Now, we're going to pick up on this point in seminars this week, and I'll give you another example where you've got to sit down with a blank piece of paper and identify the best response lines, and by extension, the mixed strategy Nash equilibrium. But what I want to do for the first part of today, and again revisit this idea, this topic of mixed strategies, is to give you another example. Work through the best response lines and identify all possible mixed strategy Nash equilibrium. And to do this, we're going to return to that game of Battle of the Sexes. And again, what we'll find in this game is that it's possible, as we've seen before, to have Nash equilibria in both pure and mixed strategies. So when we saw Battle of the Sexes before, we said that there were two Nash equilibria, where both the man and the woman went to the prize fight, and when both the man and the woman went to the opera. But that isn't all the Nash equilibria in this game. There's an additional mixed strategy that so far you've not been able to identify. And we're going to do that using that same procedure as before. So, this was the game of Battle of the Sexes. This is where the man and the woman were choosing over the venue for the night. And I know we've been through examples in seminars this week, and you had an example that looked sort of like Battle of the Sexes, where the man and the woman were choosing what venue to go to. But as we saw in seminars, this was nothing like the Battle of the Sexes. In this Battle of the Sexes, the overriding consideration for the man and the woman is that they want to go to the same venue. The only difference is the man would prefer that they went to the prize fight, and the woman would prefer that they went to the opera. And they get their worst possible outcomes where they go to different venues. So, that was the game that we saw before. I won't spend too long explaining it in any more detail, because we've seen it before and we've set it up in quite some detail. So, this was the game that we saw before. The only difference now, though, the only difference is I've put these probabilities of P and 1 minus P and Q and 1 minus Q. I've appended those to our normal form representation. Now, when we set up mixed strategies last week, I said, what were these P's and Q's? Well, these were the perceived possibilities with which the man and the woman choose what they're going to do. So, what we've got here is the probability P is the probability with which the man believes that the woman will go to the opera. So he believes that she will go to the opera with a probability of P. And by extension, if she goes to the opera with a probability of P. The rest of the time, that is with a probability of 1 minus P, she is going to go to the prize fight. And in exactly the same way, Q is the probability that the woman believes that the man will go to the opera. And by extension, if he's going to the opera with a probability of Q, the rest of the time he goes to the prize fight. And that's with a probability of 1 minus Q. So that's just setting up the example. And in all these games of mixed strategies, to identify the mixed strategy Nash equilibrium, that's the starting point. Just put those perceived probabilities in. So, that was it. Now we're in a position to do what we need to do next. So, what do we need to say? In a mixed strategy Nash equilibrium, we said that the players don't know for sure what outcomes they're going to get. Therefore, they need to look at their expected outcomes. So that's what we need to find for both the man and the woman. Their expected outcomes. What payoff can they expect given that there's uncertainty over what their partner is also going to do? So, let's look at the woman first of all. So if she chooses to go to the opera, what would her payoffs be? Well, if she goes to the opera, this is the woman here, and we're talking about the woman as the role player, so her payoffs are the first figures. Hopefully by now that is really, really being reinforced. Role player, it's the first figure. So if the woman goes to the opera, she either has a payoff of 2, or she has a payoff of 0. She will get a payoff of 2 when the man goes to the opera, and a payoff of 0 when the man goes to the prize fight. So we can calculate then her expected payoff of attending the opera. And we do that by taking the contingent payoffs and weighting them by the probability of those events occurring. So she either gets a payoff of 2 with a probability of Q, that's when the man goes to the opera, or she gets a payoff of 0 when the man goes to the prize fight. And he will do that with a probability of 1 minus Q. So for the woman, her expected payoff is 2 with a probability of Q, plus 0 with a probability of 1 minus Q. And just a simple bit of algebra simplifies that down to 2Q. So the woman's expected payoff is 2Q if she goes to the opera. And then we can do exactly the same to find her expected payoff if she chose to go to the prize fight. If the woman chooses to go to the prize fight, she either has a payoff of 0 or she has a payoff of 1. She will have 0 with a probability of Q and 1 with a probability of 1 minus Q. And that's all we've got here. 0 with a probability of Q, 1 with a probability of 1 minus Q. And so that gives her expected payoff when she attends the opera of 1 minus Q. And that's it for the woman. Now we just repeat it in exactly the same way for the man. And look at his expected payoffs. So remember, with the man, we're talking about the second number in this normal form representation. So it's these second figures here. Those are the payoffs to the man as the column player. So if the man goes to the opera, he either gets a payoff of 1 or he gets a payoff of 0. So what's his expected payoff? Well, he will get 1 with a probability of Q, 0 with a probability of 1 minus. He will get a payoff of 1 with a probability of P and a payoff of 0 with a probability of 1 minus P. 1 when the woman goes to the opera, 0 when the woman goes to the prize fight. So that's what we've got here. 1 with a probability P, 0 with a probability of 1 minus P. Simplified out, and his expected payoff of attending the opera is P. And then finally, what's his expected payoff if he chooses to go to the prize fight? We then look down this final column here. Either payoff of 0 or a payoff of 2. 0 with a probability of P, 2 with a probability of 1 minus P. That's what we've got there. 0 with a probability P, 2 with a probability of 1 minus P. Simplified out, and that gives us 2 minus 1. And for all these mixed strategies, that's always the starting point. Find the expected payoffs. If you get those wrong, it's all going to fall apart. So, taking our time, hopefully that should really, really be reinforced now. So, that's the first thing. Then, what was the next step? We said the little trick that's involved to identify the mixed strategy Nash equilibrium was to equate these expected payoffs. So for the woman, equate the expected payoffs of going to the opera and the prize fight. For the man, equate the expected payoffs of going to the opera and the prize fight. So, for the woman, when we equate the expected payoffs, we said the expected payoff of going to the opera was 2q, expected payoff of going to the prize fight was 1 minus q. So, if you equate those, and what does that mean for q? Well, that means if you just solve that through, that means when q equals 1/3, the expected payoff of going to either venue is exactly the same. And hence, if the expected payoffs are the same, what does that mean about the woman? Which of those venues would she prefer? She wouldn't mind. She would be indifferent. And that's what you need to find for the mixed strategy Nash equilibrium. That crucial probability at which the woman is indifferent. Because if she's not indifferent, she will play a pure strategy. She'll either always go to the opera, or she will always go to the prize fight. And we're not looking at the pure strategy, we want to find the mixed strategy. So that's crucial probability at which the woman is indifferent over her chosen strategy. So that means, now think about the interpretation, that means when the man goes to the opera with a probability of 1/3, that's what q equals 1/3 means. When the man goes to the opera with a probability of 1/3, the woman is indifferent over her chosen venue. That's the interpretation of that one. So, that was it for the woman when q equals 1/3. But what happens when q doesn't exactly equal 1/3? That the man doesn't go to the opera with that very, very specific probability. Well, when that's the case, the woman will not be indifferent. And why won't she be indifferent? Because one or other of these outcomes, these venues, will give a higher payoff. So, for example, when q is less than 1/3, any value, any probability of q that's less than 1/3, the woman will always get a higher payoff of going to the prize fight. And hence, if she gets a higher payoff of going to the prize fight, that is what she will always do. Now, last week, I showed you a nice little trick of a way to identify this, because I said when q is less than 1/3. Well, let's take a nice easy number. 0 is less than 1/3. So let's take that extreme. So when q equals 0, the expected payoff to the prize fight, no, the expected payoff to the opera is 2 times q, is 2 times 0. So it's 0. However, when q equals 0, the expected payoff for the prize fight is 1 minus 0. So it's 1. So going to the prize fight gives a payoff of 1. Going to the opera gives a payoff of 0. What's the woman going to do? Always go to the prize fight. That's what we've got here. And it doesn't matter what value of q that we put in, if it's less than 0, she will always get a higher payoff of going to the prize fight. And so that is what she will always do. Now at the other extreme, what happens when q is greater than 1/3? When the man goes to the opera with a probability more than 1/3. Again, it doesn't matter what value of q we adopt. It could be anything. But let's take something that's nice and easy. Let's take a value q equals 1. Makes it nice and simple for us. So when q equals 1, what's the expected payoff for the woman of going to the opera? It's 2 times q. So it's q if q equals 1. What's the expected payoff of going to the prize fight? It's 1 minus 1. So it's 0. So therefore, the expected payoff of going to the opera is greater than the expected payoff of going to the prize fight when q equals 1. Therefore, if you get more from going to the opera, that is what will always happen. And it doesn't matter what value q is greater than 1/3, that is what the woman will always do. So, now we know exactly what the woman will do, whatever the man is going to do. If he goes to the opera with a probability of 1/3, doesn't matter. Everything is optimal. She's indifferent. But if he goes to the opera with a probability of less than 1/3, the woman will always go to the prize fight. If he goes to the opera with a probability of greater than 1/3, the woman will always go to the opera. And then, to complete this, let's just do it for the man. We need to find that crucial probability for him, at which he is indifferent between the two pure strategies, opera and prize fight. So what we do is we equate his expected payoffs. Expected payoff of going to the opera was P. Expected payoff of going to the prize fight was 2 minus 2P. Equate them and work out that probability of P. Gives us 2/3. And I'll throw something in here and I'll pick it up in seminars as well. What we're looking for here is a probability. If you take these expected payoffs and you calculate a value of P or Q, and that value is negative, can a probability be negative? No. It means you've done something wrong with your algebra. If you get a value of P or Q that's greater than 1, can a probability be greater than 1? Again, no. It will indicate that you've done something wrong with your algebra. So whenever you get these values, these crucial probabilities, they've got to be somewhere between 0 and 1. So if it isn't, don't carry on regardless. It means you've done something wrong. So go back and check. So, when the woman, this is what P equals 2/3 mean. When the woman goes to the opera with a probability of 2/3, the man is indifferent over what he chooses to do, because the expected payoffs are the same. However, when P is not exactly equal to 2/3, he won't be indifferent. And if any value of P is less than 2/3, and let's take 0 for example, if you plug 0 into there, opera gives a payoff of 0, prize fight gives a payoff of 2, 2 minus 0. So, prize fight gives a higher payoff, and so that's what the man will always choose. And then lastly, if P was greater than 2/3, the woman goes to the opera with a chance greater than 2/3. For the man, the expected payoff of going to the opera is greater. So let's take the value of 1. If you go to the opera, you get a payoff of 1. If you go to the prize fight, you get a payoff of 2 minus 2 is 0. So you'll always choose to go to the opera. And that's it now. We know for the man and the woman exactly what they will do over all eventualities. And that's the starting point, and that's the easy part. This next part is where you draw your best response lines. Now they look fairly simple, and once you get the hang of them, they are really, really simple. And this is just doing exactly the same as we did last week. Okay? But I just want to go through one more example to really, really reinforce this idea. So, where you need to start from is a grid that looks like that. So if you've not got the notes in front of you, don't copy everything down. Remember, how did we set these up? We're looking at probabilities. That's all that's on these two axes. We've got probability P on the vertical axis, and we've got probability Q on the horizontal axis. And all of these games that you set up to identify the best response lines, that's what you'll need to show. Just a set of axes that show probability. Probability P and probability Q. So, given that we've got P on that axis, given that we've got Q on that axis, and just to re-emphasise something that I said last week, does it matter that we put P on that axis or Q on that axis? Absolutely not. You can put whatever you want on either axis. But the interpretation of what then occurs on that axis will change slightly. So that's where you need to be mindful. What I've put here is probability P on the vertical axis. Now what is P? If you go back to the way that we set this game up, P was the probability that the woman went to the opera. So there you go. This is the woman on that axis, on the vertical axis. Q, we set it up as Q being the probability that the man goes to the opera. So there you go. We've got the man on that axis there. Now, probability. I've already alluded to this today. Bound between 0 and 1. The minimum value that a probability can take is 0. The maximum value it can take is 1. So when we've got P and Q on these axes, that's what we're looking at. We're looking at these bounded probabilities between 0 and 1. The absolute minimum is 0 there. The absolute maximum for P is 1 there. And likewise for the man probability Q, that's Q equals 0, that's Q equals 1 there. And I've just put these labels in to remind us what Q equals 0, or P equals 0, and Q equals 1, or P equal 1 actually mean. For P, probability that the woman goes to the opera. So when P equals 1, it's at its maximum, the woman always goes to the opera. When P equals 0, that means the woman goes to the opera with a probability of 0. She never goes to the opera. She always goes to the prize fight. And that's what that label means. And exactly the same for the man. Q equals 0, man goes to the prize fight all the time. Q equals 1, the woman always goes to the opera. So that's the starting point. And then we identified these crucial probabilities of P equals 2/3 and Q equals 1/3. So I've just put these values in there on the graph. So that's, if you don't get that framework right, you don't put these labels in there, and you're not quite thinking about what's on these axes, this is where you're going to make a mistake. So that's the basic setup. Now we'll draw the best response lines in. And let's start off initially for, which one is it? Let's start off initially for the woman. Now, for the woman, what she chooses to do depends on Q, the probability with which the man goes to the opera. So, we identified that crucial probability of Q equals 1/3. And we said when Q was less than 1/3, that is, we're looking at that left-hand side of the diagram there, somewhere in that area that I'm tracing out, whenever Q was less than 1/3, we said that the woman would always go to the prize fight. She gets a higher payoff of going to the prize fight as opposed to the opera. And that is what she would always do. Not just when Q equals 0, but any value of Q as long as it's less than 1/3. She always chooses to go to the prize fight. Well, there you go. This is the woman going to the prize fight. And that's Q less than 1/3. So, whenever Q is less than 1/3, that's what the woman chooses to do. She always goes to the prize fight. And that's the first part of her best response line. That's just a graphical way of tracing out her best response. Think about it, that's what we want to identify for a Nash equilibrium. The best response of all the players. So for the woman, that's her best response. Whenever Q is less than 1/3. And we said when Q was greater than 1/3, that is, we're looking at this sort of part of the diagram here, anywhere to the right of there, the woman always chose to go to the opera. So this is the woman going to the opera. So there you go. Q greater than 1/3, that would be the next part of her best response line. And the last part, what would happen when Q was exactly equal to 1/3? Anywhere along there? What's the optimal strategy? Everything is optimal. The woman's indifferent. She could go to the opera, she could go to the prize fight, or she could adopt any other mixed strategy. They would all give exactly the same expected payoff. So everything is optimal. And therefore, that's the last part of her best response line. And there, that traces out, regardless of what the man does, or contingent, it's probably a better way to describe it, contingent upon what the man does, that traces out what the woman would choose to do, what she would choose to do optimally. And that's it for the woman. Now just complete it now for the man. Now, his best responses depends upon P, the probability with which the woman goes to the opera. And we said whenever P was less than 2/3, that is, we're looking at that sort of area here, the lower 2/3 of the diagram, we said that the optimal response of the man was to go to the prize fight. So whenever P is less than 2/3, the man will choose to go to the prize fight. Well, that's him. That's the man going to the prize fight. So, there you go. Can you see that green, is it? Just about off. There you go. We're putting that part of the line in there. So, that is what the man will do. Always choose to go to the prize fight whenever P is less than 2/3. When P was greater than 2/3, that is, we're looking at the top part of the diagram there, the man would always choose to go to the opera. And so there you go. He'll always choose to go to the opera. So that's the second part of his best response line. And then the last concluding part that finishes it all off, when P exactly equals to 2/3, what does that mean? It means the man is indifferent. Everything is optimal. Prize fight, opera, anything in between. They all give exactly the same expected payoff. And that is the final part of the man's best response line. Now, what should be fairly obvious in that diagram is those best response lines cross in 3 places. they cross here, they cross here, and they cross here. So what does that suggest? It would suggest that there are 3 Nash equilibria. And again, take a step back and think, and again I've been reinforcing this in seminars as well. Think, what does a Nash equilibrium describe? It describes that situation where all of the players are choosing a best response, where they've got no incentive to deviate, where they don't want to do anything different, given what their fellow players are doing. Well, individually, each of these lines shows what's optimal for one player. So where the lines touch or intersect will mean that both players are choosing an optimal response. What does that mean? It means it's a Nash equilibrium outcome, but only where the lines cross. So, in that sense then, our 3 Nash equilibria, there's one down in the bottom left-hand corner, where both the man and the woman play that mixed strategy of 0, 1. That is, they're both choosing to go to the prize fight. That is, they're both attending the opera with a probability of 0. They're both attending the prize fight with a probability of 1. So they're both playing the mixed strategy 0, 1. And again, it's a small point that I mentioned last week, but I did reinforce it last week, and I'll mention it again for you again this morning. Mixed strategy is not a probability. A mixed strategy is the probability distribution over which the players choose their available strategies. So, the mixed strategy is 0, 1. Go to the opera with a probability of 0. Go to the prize fight with a probability of 1. So both the man and the woman play that mixed strategy, 0, 1. So the man chooses 0, 1. The woman chooses 0, 1. That's our first Nash equilibrium. And that accords with the idea where they both went to the prize fight. The second Nash equilibrium, there you go, up in the top right corner there, again with these best response lines intersect, is where both the man and the woman attend the opera. That is, they go to the opera with a probability of 1, and they go to the prize fight with a probability of 0. So they're both playing the mixed strategy 1, 0. And it's those 2 Nash equilibria that we saw when we identified this game in its normal form. We wrote it down, we put the circles around there, and we said the 2 Nash equilibria, or the Nash equilibria actually in pure strategies, where they both went to the opera, or they both went to the prize fight. We've identified those in this diagram here. However, when we looked at that game in its normal form, those were the only 2 Nash equilibria we could identify. What we weren't able to do is identify that Nash equilibrium there in the middle. And this Nash equilibrium is where the woman plays the mixed strategy of 2/3, 1/3. That is, she goes to the opera with a probability of 2/3, and hence the prize fight with a probability of 1/3. So that's her mixed strategy there. 2/3, 1/3. The man, though, in this third Nash equilibrium, plays the mixed strategy where he goes to the opera with a probability of 1/3. And, by extension, he then goes to the prize fight with a probability of 2/3. So that is the third and final Nash equilibrium in that game. And it's only by using the best response lines that we're able to identify all of the Nash equilibrium. What I now want to do is move on to our next topic, and that, by the title that you've got here, relates to dynamic games of complete information. So, all of the games that we've studied so far have been static games. They've been games where players move simultaneously, where they choose their actions at the same time. Now, though, we're going to move into a completely different, a new class of game, where players move sequentially, where they take it in turns to move. So that will change. But what is still the same, though, is we'll still look at games of complete information. And what that means for dynamic games is that players, when they're about to move, they have a complete and accurate history of the game that's unfolded before them. There are no hidden moves in these games, actions are not unobserved. So the players take it in turns, they move sequentially. That is what we mean by a dynamic game. So static games, players move at the same time. Dynamic games, they take it in turns. But what isn't going to change though is the fact that these will be games of complete information. Now we will change that in one of our very, very last topics when we start looking at Bayesian Nash equilibrium, where players, even though they take it in turns, where there isn't complete information, where players don't perfectly observe what's happening. But that is somewhat more difficult, that's somewhat more technical, and there's an awful lot more maths in it. So that's right at the end of the course. So for the moment, don't worry about it. So, start off, just dynamic games. And what are the basics of dynamic games? And how do we represent these dynamic games? And how do we identify the outcomes in these dynamic games? All done in the context of perfect and complete information. So, that's what we're going to do in this next topic. And the way that I'm going to introduce you to this and start the ball rolling and expose you to some of the basic concepts is I'm going to give you a very, very simple game. So in the same way, when we looked at static games, I gave you some classic games, such as The Prisoner's Dilemma or Battle of the Sexes. And absolutely, I would expect you to be able to reproduce these very, very quickly and accurately whenever we talk about static games. That's got to be your starting point. Well, in these dynamic games, again, I'm going to give you a very, very simple game, but you need to understand it implicitly. You need to be able to reproduce it in a whole host of scenarios. If you can't, not only will you struggle in lectures, but the chances are you're also going to struggle in the exam. So for dynamic games, this next game that I'm going to give you is absolutely crucial. You need to understand what's going on. And this game that I'm going to give you is a game of market entry. And in this game, there are two players. And these two players are two firms. We have an incumbent firm which is already producing its output within a market. And we also have a potential entrant or a challenger. And what the challenger is thinking about doing is entering the market and setting itself up in competition against that incumbent firm that's already within the market. So that's the nature of our game. But the way that I've described it, you can see is a sequencing of moves. And the player who chooses first is that potential entrant, is the challenger. The potential challenger then makes that choice. What do I need to do? Do I enter the market? That is, do I choose that strategy of in, or do I stay out? So that's the first part of this game. The potential entrant, the challenger, chooses over its available strategies of in or out. Does it stay outside of the market, i.e. the status quo isn't affected, or does it enter into the market and set itself up in competition against the incumbent firm? So that's the first choice. However, if that challenger does choose to enter the market, then it comes a decision that needs to be made by the incumbent firm. What does it do? It's producing within its market, and then a challenger enters. And it can do one of two things. Firstly, it can fight market entry. It can cut its price. It cannot concede the market to that challenger. So it adopts an aggressive pricing strategy, if you like. It could be a whole multitude of what it could do, but absolutely it fights market entry. That's one possibility. The other possibility for the incumbent firm is if the challenger enters the market, it does nothing. It acquiesces to the firm. It allows it to enter the market, and it doesn't retaliate in any way whatsoever. So that's the game. Very, very simple. Potential entrant thinks, do I enter in or stay out? If it enters in, then the incumbent firm needs to make a choice. Does it fight or does it acquiesce? Well, that's the game that we've got. Now, let's think about the outcomes and the preferences on what these two firms prefer? Well, absolutely. The worst possible scenario for both firms is that they get involved in competition against each other, that there's some sort of price war against each other. So that's the worst possible scenario. What they wouldn't want is for the entrant, the challenger, to go into the market and for the incumbent to fight. That's the worst for both firms. If that happens, the profits of both firms will be driven all the way down to zero. So that's their worst possible outcome. Neither firm wants that. However, there's a difference in the preferred outcomes for the challenger and the incumbent. The incumbent would rather that things didn't change. It's happily producing within the market as it stands. It's got high profits. It doesn't want the challenger to enter the market and either be involved in a fight nor to erode any of its profits anyway. So the incumbent wants the challenger to stay out. That's its most preferred outcome. However, for the challenger, this potential entrant, its most preferred outcome is for it to enter the industry and for the incumbent firm to acquiesce. That is more profitable than staying out of the market altogether. And obviously, it's more profitable than being involved in some sort of price war as well. So, there's a common ground on what they don't want, and that's to be involved in a fight with each other. But the incumbent wants the challenger to stay out. The challenger wants to enter the market, but for the incumbent to acquiesce. So what we've described here is a strict ordering of these preferences. We know the least preferred, we know the most preferred, and everything in between. And all this is doing, again, I know I keep on saying it in today's lecture, but this is just reinforcing the sort of things that we did in our seminars this week. That we've set up games discursively, now it's over to you to represent them. Well, we are going to represent them, but we're not going to represent them in its normal form, as we did with static games. Instead, what we're going to do is represent this dynamic game in what's called the extensive form representation, using this game tree that we've got here. Now, in these extensive form representation games, what we'll do is start right at the top here. And we'll start where the first player makes its move. And in this game, the first player to make its move is the challenger. And the challenger chooses over two potential strategies of either in or out. Now, if the challenger does choose out, the game ends and the players get their payoffs. Now, in these extensive form games, there's no right or wrong way in which you can present the payoffs. What I will do, and some people do different things, what I will do, not only in this example, and all of the examples that I'll ever give you in lectures, but also in seminars and the way that I'll present these things in exam as well, I will always present the payoffs in the order in which the players move. So, here, the challenger is moving first. And hence, if the challenger chooses out, the game ends. And the players receive their payoffs. And these payoffs are 1 to the challenger, because he's the one who's moving first, and a payoff of 2 to the incumbent, because he's the one who moves second. So that is where the game finishes there with those respective payoffs. However, if the challenger didn't choose out, but rather chose in, then we come to the incumbent's choice node. Then there's a decision for the incumbent to take. Does it acquiesce or does it fight? Does it concede the market to the challenger or does it choose to fight? Well, either scenario, if it chooses to acquiesce, again the game finishes and the payoffs are 2 to the challenger and 1 to the incumbent. If, though, the incumbent firm chooses to fight, the payoffs are 0 to both of the firms. But that is where the game ends. So, what we've got here then are three potential outcomes in this game. And we can describe these outcomes as terminal histories. And all a terminal history is, all it does is it traces out the series of actions until the game ends. And so, our three potential endpoints, three potential outcomes for this game are in acquiesce, which results in a payoff of 2 to the challenger and 1 to the incumbent. That's one potential outcome. The other, another potential outcome, another potential terminal history, is in fight, where the challenger chooses in and the incumbent responds by fighting. And that will lead to a payoff of 0 for both players. Now the third potential terminal history, third potential outcome, is out, where the challenger just stays out of the market altogether, and this results in a payoff of 1 to the challenger and 2 to the incumbent. Now, as I've described this, I've said these figures. We've got these pairs, so 0, 1 and 2. All you need to think about these are they just rank the outcomes. They represent the preferences of the two firms. So we've got 0, 1 and 2. It doesn't really matter what figures you put in there, as long as they rank them in the same way. So the least preferred outcome is 0. So both firms don't want that outcome there, where they get involved in a fight with each other. However, the most preferred, and this is important moving forward, the most preferred outcome for the challenger is it enters the market. This is where it gets its 2. It enters the market and the incumbent firm acquiesces. That's its most preferred outcome. For the incumbent firm, though, its most preferred outcome is here, where the challenger stays out altogether. So that's our game of market entry. And that is how we represent it in its extensive form. And now we can see the dynamics of the game, how players take it in turns to move. But there's no point, as I've said before, there's no point setting up a game if we can't say anything about the most likely outcome of that game. Well, if you look at that game there, I won't give you the formalities of how we identify the outcome at the moment, but if you look at it and just take a step back and think about the thought processes of the challenger and the incumbent, I'm hoping that it should be fairly clear to you what the outcome of this game would be. And what do you think? Who's making the first move? It's the challenger. And the challenger is thinking to itself, well, what would happen if I enter this market? The incumbent has got a chance to acquiesce or fight. Now, what's it not going to do? It's not going to want to harm itself. It's not going to want to fight, because that will give it its least preferred outcome. It's got an option of not fighting me. It makes no sense whatsoever to adopt that strategy or follow that strategy of fight. So that will be the incumbent's thought processes. If I enter the market, there's no way the incumbent is going to turn around and fight me. It's not going to do that. Therefore, the challenger knows if it enters the market, the incumbent is going to acquiesce. And so it then says, well, do I enter the market knowing that the incumbent will acquiesce, or do I stay out? And it looks at its payoffs. Well, it's more profitable for me to enter the market for the incumbent to acquiesce, rather than staying out and getting nothing. So, that's what it will choose to do. It will enter the market knowing the response it will be met with. And that is the outcome, that will be the outcome of this game. Now, that process that I've described to you is known as backwards induction. Now, I've just thrown the idea at you for the moment, and in 10-15 minutes we're going to go through this in an awful lot more formality, just to run through how the process works. But for the moment, I just want to throw the idea out there at you that the outcome of this game, if you think about it intuitively, the outcome of this game is going to be where the challenger enters and the incumbent acquiesces. That's what the outcome is going to be. So we've got 3 possible outcomes, but that's the one that will be chosen. But we've already seen a way of identifying outcomes in games. And I gave you the idea that a Nash equilibrium leads to the most plausible outcomes and the only viable outcomes in games. So what does that mean for this game here? Where's the Nash equilibrium? Is that outcome that I've identified the Nash equilibrium? Well, when we look at games in their extensive form, it's not easy to identify a Nash equilibrium. But we know what to do. If we take that game and we translate it and represent it in its normal form, then we can go through our tried and trusted procedure. Going through and identify and put the best responses, put the circle around them, and see where the Nash equilibrium lies. So, that's what we'll do. We'll take that game of market entry, and we'll translate all that information into this normal form representation. So, we've got our 2 players. We've got the challenger, who chooses over the potential strategies of in or out. And we have the incumbent, who chooses over the potential strategies of acquiesce or fight. Now, if the challenger chooses in and the incumbent acquiesces, the payoffs are 2 to the challenger and 1 to the incumbent. If it chooses in and it fights, payoff of 0 to both. So if the challenger chooses to enter the market, the payoffs are different, depending upon what the incumbent does, whether it acquiesces or whether it fights. And these are just the payoffs that we represented previously. 2-1 or 0-0. However, what happens if the challenger stays out? The payoff is 1 to the challenger and 2 to the incumbent. Doesn't matter what the incumbent does, the payoff will be exactly the same. It's going to be 1-2. So that is the game in its normal form. So, how would we identify the Nash equilibrium? Well, it's fairly straightforward. If the incumbent chose to acquiesce, the best response for the challenger is to choose. Whoops, let's do it the other way around then. If the challenger chooses in, what does the incumbent want to do? Does it want to acquiesce and get a payoff of 1, or fight and get a payoff of 0? It will choose to acquiesce. So you put that circle around it. Slightly different to the way that I've done this previously, because now I'm doing the column player first, as opposed to the row player. But we're talking about the incumbent's optimal strategy. So we're looking at the second figure. So, challenger chooses in. Does the incumbent choose acquiesce with a payoff of 1, fight with a payoff of 0? We've already said the incumbent firm doesn't want to fight. If it does so, it gets its lowest possible payoff. So, the optimal response is to acquiesce. If, though, the challenger stayed out, would the incumbent acquiesce and get a payoff of 2, or fight and get a payoff of 2? Doesn't matter. Both give exactly the same. So I'll put a circle around both of them. They're both optimal responses. And then lastly, for the challenger, what are his optimal responses if the incumbent chooses to acquiesce? Does it choose to enter the market and get a payoff of 1, or stay out and get a payoff of, enter the market and get a payoff of 2, stay out and get a payoff of 1. Obviously 2 is preferred to 1. So again, that circle around denotes the optimal response. And then lastly, were the incumbent to fight, is the challenger going to choose to enter and get a payoff of 0, or stay out and get a payoff of 1? If the incumbent was going to fight, it would rather stay out and get a payoff of 1. So, in this game, there are 2 Nash equilibria. One in the top left, where the challenger chooses to enter and the incumbent chooses to acquiesce. Well, that was the exact same outcome that we argued through intuitively 5 minutes ago. That was the outcome that I said to you was identified by that process of backwards induction. So that outcome is a Nash equilibrium. So that all augurs well. That sounds good. Okay, it's not a problem. But there is, though, a second Nash equilibrium, where those 2 circles coincided. And that was down in that bottom right-hand corner. So there's a second Nash equilibrium where the challenger chooses to stay out and the incumbent firm chooses to fight. So, two Nash equilibria. One, you get the idea of that. That's the one identified by that process of backwards induction. Hopefully there should be no problems with it. But that second one, and I want you to really, really reflect on what that Nash equilibrium means and what it suggests. Because that Nash equilibrium, that Nash equilibrium there is really, really problematic. What you need to do is think, why is it problematic? Think about what a Nash equilibrium entails. It means no player has an incentive to do anything different. And were you to ask the challenger, if you knew the incumbent was going to fight, would you want to stay out? What would the response be? Yes or no? So if we said to the challenger, if you knew the incumbent was going to fight, would you want to stay out? Yes or no? Yeah, you do. Absolutely. If you knew the incumbent was going to fight, that, as a Nash equilibrium, makes perfect sense. But what does it suggest, though? It suggests that there's some sort of commitment there. The way that I phrased the question, if you knew that they were going to fight, does the challenger know the incumbent is going to fight? Can the incumbent convince the challenger that it's going to fight? Well, no. Because even if the incumbent firm says, I'm going to fight, if you enter this market, absolutely, I'm going to fight you. And that will drive your profits all the way down to zero. It suggests a commitment, which we haven't said anything about commitments being made anyway, but even if that commitment was there, it completely and utterly ignores the dynamics of the game. It suggests a once and for all strategy. It suggests the idea that the incumbent firm says, whatever happens, I'm going to fight market entry. But as soon as market entry occurs, what is it optimal for the incumbent firm to do? It's not to fight, it's to acquiesce. So you can see that whole process of using that as a Nash equilibrium, of saying that it's a plausible outcome, causes so many problems. It suggests this commitment. This commitment isn't credible, and it completely ignores the dynamics of the game. And that's the whole point about these dynamic games, that there is dynamics in there, that players do change what they do, what they choose to do, as the game unfolds. And so for all of these reasons, that Nash equilibrium, as we've described here, is really, really problematic. And it's not sensible to adopt this idea of a Nash equilibrium in dynamic games. Therefore, we're going to need something different, a little bit something else, that moves away from this simple idea of a Nash equilibrium that I've given you so far. And that something else is going to be the ability to identify not just a Nash equilibrium, but rather a subgame perfect Nash equilibrium. So you should all be familiar and comfortable at this stage what a Nash equilibrium is, and all the incentives that players face in a Nash equilibrium. But what is a subgame perfect Nash equilibrium? That's the added part that we need to address. Now, this whole course is about game theory, and you know what games are. So that, again, is going to be problematic. But what is a sub-game? Well, a sub-game, just to give you a very, very simple quote definition, a sub-game is that part of a game that exists or remains after an action has occurred. And in that game of market entry that we've seen, there are actually two sub-games. Now, the first sub-game is just a technicality, because in all games described in their extensive form, the game in its entirety is always the first sub-game. However, there's also a second proper sub-game. And this proper subgame are the choices that occur after the challenger has chosen to enter the market. So that's the part of the game that's unfolded. The challenger has entered the market. Then we came down to the incumbent's choice now, where the incumbent is choosing between acquiesce and fight. So that is the subgame. So, for an outcome to be subgame perfect, the strategy needs to be an optimal strategy in all subgames. Not just the game in its entirety, but all of these mini-games that are played as well. That's what we need to find. We want to find a Nash equilibrium where players don't have an incentive to deviate. But that outcome, the strategies within that game, need to be optimal strategies in all subgames. And if you think about it, we said that the Nash equilibrium of out-fight, we said that was problematic. Why is it problematic? Because it's not a subgame perfect outcome. Because that strategy of fight is not subgame perfect. That subgame that we saw, where the incumbent is choosing over acquiesce and fight, is it ever optimal in that subgame for the incumbent firm to fight? Hopefully you should know that the answer is no. After market entry has occurred, the optimal thing that the incumbent can always do, or should always do, is to acquiesce, is not to fight market entry. And so the strategy of fight is not optimal in that subgame that takes place. And hence, the Nash equilibrium of outfight itself cannot be subgame optimal, because the strategy of fight is not optimal in all subgames. And hence, even though that was a Nash equilibrium, it is not a subgame perfect Nash equilibrium. And in dynamic games of this sort, it means we can then rule it out as a plausible outcome. So that's what we're going to need. That little bit of something else that we're going to need in these dynamic games. Not just the concept of a Nash equilibrium, because certain Nash equilibria that ignore the dynamics of the game are not plausible. Games of this sort, we need to identify subgame perfect Nash equilibrium. That is, Nash equilibria that involve strategies that are optimal in all subgames. So, for the moment, I would be surprised if you understand perfectly everything I've said. There were probably still some ideas floating around. Don't worry. What I'm now going to do is return to this idea of how we identify a subgame perfect Nash equilibrium. And we'll use a very, very simple and clear-cut rubric. Whenever we have dynamic games, this is what you need to do. And once I've given you this rubric, then I'll tell you a common mistake that students make. Okay? So, this whole idea of how do we find subgame perfect Nash equilibrium? Well, it goes back to that concept that I alluded to previously. I said in our game of market entry, when we thought through it intuitively, the outcome that we identified was via a process of backwards induction. And it's this process of backwards induction that you need to follow to identify the subgame perfect Nash equilibria of any game. As its name suggests, you work backwards. You don't, even though we set the games up and said players take it in turns to move, and then as the game unfolds, they change their actions. Backwards induction means you go right to the very, very end of the game and then work backwards towards the beginning. So, the process of backwards induction to identify subgame perfect Nash equilibria works in the following way. We go right to that very last set of subgames that are being played. Right to the very, very end of the game. And then, in those subgames, we look to identify the optimal strategies of those players in those subgames. And we take those optimal strategies as given. We said, okay, in these subgames, this is what those players are going to do. Right? We take those actions as given and move to the preceding round of subgames that are being played. And then we do exactly the same. In that preceding round of subgames, we look to identify the optimal outcomes of the players, the optimal strategies, I should say, of the players in those subgames in the penultimate round. And again, we identify those optimal strategies and we take them as given. And then we go to the preceding round of subgames. Now, there can be as many subgames and rounds of subgames as you like in this. What I'm going to do in the examples that I give you here, and indeed the examples that you're going to do in seminars, the examples that I'm going to expect you to be able to do in the exam, will only be concerned with 2 rounds. Okay? But the basic principle is still going to be there. So, start at the end, take the strategies given, and then move backwards towards the beginning of the game. I can't emphasise enough how that's what you've got to do. And even in an exam, if I was asking you the question, and I've told you about this in seminars, importantly, I would say with explanation, with accompanying discussion. Even if you might represent a game, an extensive form game, and you correctly identify the subgame perfect Nash equilibrium, if the whole process, the way that you've described it, you start from the beginning of the game and then work towards the end, actually, that shows me no understanding at all. That shows me that you don't understand this very, very important concept of backwards induction. So you've got to go, and your discussion as well, has got to go to the end of the game. So, that's our fairly straightforward rubric. What I'll now do is give you an abstract example, and we'll just apply that rubric to that game. And again, if you look at that, okay, there's a few more well, there is one extra sub-game in that game than we saw previously. But again, given that it's an abstract game, it's not obvious to see what the outcome of that game would be, what the sub-game perfect Nash equilibrium of that game would be. Hence, we need to use backwards induction. So, our process then, go right to the end of the game. Go to those final round of sub-games. Well, the final round of sub-games are here. We've got one on the left there, where player 2 is choosing between C and D. We've got one here on the right, where player 2 is choosing between E and F. And within the game, whether we come down this branch on the left or this branch on the right, depends upon what player 1 does in the first instance. So, this is the dynamic nature of our game. But backwards induction says, go to the end and find those optimal strategies in those final rounds of subgames. So, player 2 is choosing over C or D. What would player 2 do? Choose C or D? Tell me. What would player 2 do? Got one C there, or D? Look, there's a 3 there. What would player 2 do? C or D? Can you all see that player 2 would choose C? We're talking about player 2, and what I said about the order in which we've got these payoffs, the order in which the players move. The first figure is the payoff to player 1, the second figure is the payoff to player 2. So, player 2 chooses C and gets a payoff of 1, or chooses D and gets a payoff of 0. What's player 2 not going to do? Not going to choose D. So we'll remove that as a viable option. So there you go. Take that away. And that's all we want in that particular subgame. Now moving to the right, where player 2 is choosing between E, that gives a payoff of 2, or F, that gives a payoff of 3. Much rather 3 to 2, and hence it will never choose, player 2 would never choose E. So again, we can remove that as a possible strategy. And that's it for our final round of subgames. So we take these actions of C and F as given, And then we move to the preceding round, where player 1 is choosing over A or B. Now player 1, if he chooses A, knowing that player 2 will choose C, will receive a payoff of 2. If though he chooses B, knowing that player 2 will choose F, we will receive a payoff of 1. So he chooses over 1 or 2. Much rather 2 as opposed to 1, and hence he won't choose B. And that leads us down this terminal history here of A, C. Player 1 chooses A, followed by player 2 choosing C. And that is our subgame perfect Nash equilibrium. Or I'll use these terms interchangeably in lectures. I'll also describe that as a subgame perfect outcome. Any subgame perfect outcome will always also be a Nash equilibrium. But remember, the flip side of that is not also true. Every Nash equilibrium doesn't have to be a subgame perfect outcome. What we did, we represented that game of market entry. We had 2 Nash equilibria. But only one of them was a subgame perfect outcome. And that is our subgame perfect Nash equilibrium. And that's what we identify, that's what we need to identify in dynamic games like this. So what I want to do is go back to this idea of that game of market entry and look at commitment. This was the game that we saw. The challenger choosing in and out. Then the incumbent responds by choosing between acquiesce and fight. How would we identify the subgame perfect Nash equilibrium, the subgame perfect outcome? Well, we'll go through this formally now, as opposed to that intuitive procedure that we did previously. Using the process of backwards induction, we go to the end of the game, where the incumbent is choosing between acquiesce and fight. If the incumbent chooses acquiesce, it gets a payoff of 1. If it chooses fight, it gets a payoff of 0. Therefore, we know that it will never ever choose to fight. So we remove that as a viable option. Therefore, that's it. Then we move to the preceding round. That's where the challenger chooses in, knowing the incumbent will choose acquiesce and gets a payoff of 2, or it stays out and gets a payoff of 1. So the challenger says, do I want a payoff of 1, or do I want a payoff of 2? Well, I'd much rather 2 as opposed to 1, and hence, it won't choose out. And so, that's what we said previously. That subgame perfect outcome, or that subgame perfect Nash equilibrium, is in acquiesce. That's what we said previously. But what I want you to do, I'll set this up because I don't want to rush this last part because it is important, but I'll just set this up ready for next week. And what I want you to think about are the outcome that we get, that subgame perfect Nash equilibrium outcome that we get, and look what it means for the 2 players. Is the challenger happy with that outcome? Well, yeah. What's the challenger's most preferred outcome? Where it gets its 2, where it enters the market, and the incumbent acquiesces. So that's where it gets its payoff of 2. The incumbent, though, does he get his most preferred outcome? No, he's only got a payoff of 1. What the incumbent would much rather happen is that the challenger stayed out of the market altogether. If that happened, he would get a payoff of 2. And this is the part we're going to pick up next week. It's all to do with commitment. If only the incumbent firm could convince the challenger that it entered, it would fight market entry. Because if the incumbent could convince the challenger, what would the challenger then do? If it knew the incumbent was going to fight, would it enter the market? No. If it knew it was going to fight, it wouldn't. It would rather stay out. And if that was the case, the incumbent firm could then get its most preferred outcome.